Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Our channel is dedicated to bringing you the latest innovations and insights in green energy, including cutting-edge developments like green hydrogen. Whether you're a sustainability veteran or just beginning your journey, we have something for everyone. Join us on this channel to explore inspiring projects for a sustainable tomorrow. We bring you the latest in renewable energy, sustainability, and cutting-edge technologies. And don't forget, for more in-depth information and resources, visit our website and subscribe to our newsletter for the latest updates and exclusive content. Producing green hydrogen is only half the battle. Storing it safely and transporting it efficiently are equally critical for building a global hydrogen economy. In this episode, we'll dive into the logistical challenges of hydrogen, compression, liquefaction, pipeline transport, and trucking, and reveal how AI dramatically improves safety, forecasting, and cost efficiency across the supply chain. By the end, you'll understand why intelligent logistics is as important as electrolysis for unlocking green hydrogen's full potential. Hydrogen's physical properties present unique storage and transportation hurdles. Its low volumetric energy density, about 0.089 kilograms per cubic meter at standard temperature and pressure, means we must compress it to high pressures, 350 to 700 bar, or liquefy it at minus 253 degrees Celsius to store meaningful amounts. Alternatively, we can chemically bind hydrogen to liquid organic carriers, LOHC, or metal hydrides, but these methods often add complexity and cost. Whichever option is chosen, each step, compression, liquefaction, or chemical binding, adds capex and opex. Compression accounts for 10 to 15% of production energy. Liquefaction can consume up to 30% of the hydrogen's energy content. That's where AI-driven optimization becomes invaluable. Machine learning models trained on thermodynamic data, compressor performance metrics, and real-time operational parameters can continuously tweak compression sequences to minimize energy use and maximize throughput. For instance, AI can determine the optimal number of compression stages and intermittent cooling cycles, balancing the trade-off between higher pressures and diminishing returns on energy consumption. Once hydrogen is compressed, it faces two main transport options: pipelines or truck/trailer shipments. Hydrogen pipelines exist in certain regions, like the US Gulf Coast or Germany's industrial heartland, but they're far less widespread than natural gas networks. Retrofitting existing natural gas pipelines to carry hydrogen requires careful material assessment. Hydrogen can embrittle certain steels, leading to possible cracks and leaks. Pipelines must be made of hydrogen-compatible alloys and undergo rigorous integrity checks to prevent embrittlement. AI helps by analyzing vast datasets from sensor arrays, pressure transducers, acoustic monitors, ultrasonic inspection devices, to predict where and when embrittlement might occur. Predictive models can recommend maintenance or pipe replacement schedules before a failure happens, significantly reducing downtime and safety risks. In regions without pipeline infrastructure, hydrogen is trucked either as compressed gas, at 200 to 250 bar, in Type 3 or 4 cylinders, or as liquid hydrogen, LH2, in cryogenic tankers. Each mode has its own logistical constraints. Compressed gas offers simplicity but limited capacity, around 150 kilograms per trailer, while liquefied hydrogen provides higher density, around 6 kilograms per cubic meter, but requires more energy for cooling and specialized cryogenic handling. AI plays a key role in route optimization, evaluating real-time traffic data, weather conditions, especially for cryogenic shipments, and customer demand schedules to minimize transit times and ensure timely deliveries. Platforms like IBM's Watson Freight and Shell's AI-powered logistics dashboards can analyze thousands of possible routes and dispatch combinations each hour, increasing on-time delivery rates by up to 30%. Demand forecasting is another critical AI application. Industrial customers, such as refineries, chemical plants, or steel mills, consume hydrogen according to production schedules that can vary daily or even hourly. AI models ingest data streams, historical consumption, order books, process parameters, and market trends, to predict demand at each off-taker location. Accurate forecasts allow producers to adjust electrolyzer output or coordinate shipments more precisely, avoiding both shortages and costly overproduction. For companies operating multiple hydrogen production sites, AI can optimize production portfolios by diverting hydrogen from low-demand regions to high-demand zones, factoring in transportation costs and time windows. Hydrogen storage at scale often involves salt caverns or decommissioned natural gas reservoirs. Salt caverns can hold thousands of tons of hydrogen at moderate pressures, about 100 to 200 bar, making them ideal for seasonal or strategic storage. However, managing underground storage introduces geomechanical risks, cavern collapse, unintended leaks to surrounding formations, and temperature-induced rock stresses. AI systems trained on geospatial and geomechanical data, such as seismic readings, well logs, and cavern pressure histories, can detect early signs of structural anomalies. Machine learning algorithms can perform continuous surface deformation monitoring using satellite radar data, in SAR, combined with wellhead pressure telemetry. These insights enable operators to adjust injection/withdrawal schedules and maintain cavern integrity, reducing the risk of catastrophic events. In addition to forecasting and route optimization, safety monitoring benefits greatly from AI. Hydrogen is odorless, colorless, and diffuses rapidly, making leaks difficult to detect with human senses. Modern storage facilities and pipelines deploy distributed fiber optic sensors, DAS, distributed acoustic sensing, that capture acoustic signatures along the entire length of a pipeline or storage cavern. Machine learning models, often convolutional neural networks, analyze acoustic waveforms to distinguish between normal fluid flow noise and anomalous leak signals. Early detection ensures prompt shutoff, minimizing product loss and safety risks. Similarly, in refueling stations, AI-enabled sensor fusion integrates data from thermal cameras, LiDAR, and gas detectors to identify hydrogen buildup in real time, triggering automated ventilation or emergency shutdown. Hydrogen trading platforms, though nascent, will become more prevalent as the market matures. Just as natural gas is traded on hubs like Henry Hub or TTF, hydrogen markets require transparent pricing, standardized contracts, and reliable logistical data. AI and blockchain can jointly facilitate these emerging markets. Smart contracts, self-executing agreements coded on a blockchain, can automate settlement once specified conditions, for example, volume delivered, purity level, are met. AI algorithms can verify sensor data against contract terms, temperature, pressure, flow rates, and trigger payments instantly. This combination reduces counterparty risk and administrative friction, encouraging broader participation from industrial buyers and financial institutions. To illustrate these concepts, let's examine a hypothetical regional hydrogen network in the U.S. Midwest. Imagine 3 electrolyzer plants, one in Iowa powered by wind, another in Texas powered by solar, and a third in California powered by a mix of renewables. Each plant can produce up to 50 megawatts of hydrogen. AI systems across these plants coordinate with a network of salt caverns in Kansas for bulk storage and a fleet of hydrogen trailers that serve regional off-takers, refineries in Oklahoma, steel mills in Indiana, and a nascent hydrogen fueling station network in Michigan. When wind generation in Iowa peaks at night, AI ramps up electrolyzers there and sends hydrogen to Kansas for storage. As morning approaches, solar in Texas surges, AI shifts production south and dispatches trailers toward oil refineries reporting midday demand spikes. Simultaneously, the California plant reduces its output to avoid grid overloading, storing power instead in batteries for local grid services. This tri-state coordination happens in real time, with AI optimizing near-term decisions, hourly scheduling, and longer-term planning, seasonal storage management, using machine learning models trained on a year's worth of generation, demand, and price data. The result is a robust, flexible hydrogen supply chain that maximizes renewable utilization and meets diverse demand profiles, industrial heat, fuel for heavy trucks, and refueling of backup generators for critical infrastructure. As more electrolyzer capacity comes online, and as hydrogen pipelines interconnect production hubs, AI's role will only expand, managing cross-border flows, integrating with power market bidding, and coordinating with downstream applications like ammonia synthesis or direct injection into steel plants. In Episode 6, Money, Geopolitics, and New Value Chains will widen our lens to explore the economic and geopolitical impacts of AI hydrogen integration. We'll analyze how trade dynamics shift when countries export or import green hydrogen, how new alliances form around critical materials and technologies, and how economic opportunities, job creation and industrial competitiveness emerge. You'll learn why some nations, once reliant on fossil fuel exports, may pivot to become clean energy champions, reshaping global power dynamics. Before we close, here's your quick action: evaluate your region's logistics network. If you're a project developer, map out potential hydrogen sources, electrolyzer sites near renewables, against key demand centers. Identify gaps where pipeline investments or truck routes are needed. Use publicly available data, wind speed maps, grid interconnection costs, industrial offtake volumes, to sketch a preliminary supply chain. Then, consider which AI tools, predictive maintenance, route optimization, demand forecasting, could reduce your OPEX by 10 to 20%. Thank you for watching episode 5 of Why Green Hydrogen is Critical in the Global AI Race. Don't forget to subscribe, tap the notification bell, and leave a comment telling us which hydrogen logistics challenge, pipeline integrity, trucking efficiency, or cavern storage you think AI can solve first. We'll be answering questions and sharing resources throughout the series. Join us next time as we examine how AI and hydrogen converge to reshape economics and geopolitics in episode 6. Until then, keep analyzing, stay strategic, and remember, intelligent logistics are the backbone of a thriving hydrogen economy. Thanks for tuning into the ReneEnergy.com YouTube channel. We trust you found this episode enlightening.